Today I will be talking about moles. Mole is just a unit of measurement, like any other unit of measurement such as meter. A mole represents the number of particles in one specific substance. The exact value of a mole is equal to the number of particles in 12 grams of carbon-12, which is 6.02 times 10 to the power of 23. This is also called Avogadro's number. However, the unit is slightly different. Oh, sorry. For Avogadro's number, the unit is particles per mole, also written as moles times -1. The reason why it's called Avogadro's number is because this man, Avogadro, initiated the theory that if you have the same volume of gas at the same temperature and room and pressure, they would contain this equal number of molecules. Yes, that man didn't actually discover the value 6.02 times 10 to the power of 23, but they named it after him to honor his contribution to chemistry. Now, I have a question to ask you. Do you know what's the mass of a 1 mole of a substance is called? It's called molar mass. So, say if you have this substance, calcium hydrocarbonate, how would you calculate its molar mass? Well, you'll get given a data booklet during your exam. It would have the periodic table on it. So you spot where calcium is on the periodic table and where oxygen and hydrogen are on the periodic table. So for calcium, its molar mass is sorry. For calcium, its molar mass is 40. And for oxygen and hydrogen respectively, it's 16 and 1. So since you have 1 calcium in this compound, you do 1 times 40, and since you have 2 hydrogen ion, you just do 1 and 2 times brackets 1 times 16, which is molar mass of oxygen inside the bracket, times 1 times 1. Oh, sorry, plus 1 times 1, which is the molar mass of hydrogen inside the brackets. And you would get 74 as your answer. This is the molar mass of calcium. So, is molar mass useful in any way? It is. When you are calculating a percentage composition, you just do molar mass of an element divided by molar mass of the compound, and then you'd get a number, which is the percentage composition of that element in that compound. So say if you have this this compound called magnesium oxide. Its formula is MgO. And the molar mass of Mg on the periodic table is 24. And the molar mass of oxygen on the periodic table is 16. So what's the percentage composition of magnesium and oxygen respectively in the compound? You would do, for magnesium, it would be 24 divided by 24 plus 16, because 24 plus 16 would be the total molar mass of that compound. And then it's equal to 60%. And for magnesium, you could do 16 divided by brackets 24 plus 16, which is 40%. And to just for a final check, you could plus a two element percentage composition if they are if you add them and you get 1, it would mean that you calculated correctly, well, in most circumstances. Now let's move on to the applications of moles in chemical formulas. One reaction that's very commonly seen is the reaction of magnesium. And oxygen. Oh, sorry, let's go back. The formula involving 3 variables: amount of substance, mass of the substance, and molar mass of the substance. They have this relationship where amount of substance equals the mass of substance divided by the molar mass of the substance. If you represent them in letters, it would be N equals M divided by capitalized M. And the units for those variables individually is amount of substance, mole, mass of the substance, grams, molar mass of the substance, grams per mole, which is written as G mole times -1. And if you know any two of the 3 variables, you can calculate the value of the 3rd variable. And if you rearrange the formula, you would get M equals N times capitalized M. Capitalized M equals M divided by N. You know how you have two substances, or maybe not two, you have reactants and your products for a chemical reaction. How moles apply in chemical reactions is that it's helpful when you want to figure out which reactant is excess or limited, and if you want to calculate the mass of substances. So here we have this formula: magnesium reacting with oxygen producing magnesium oxide. It's already balanced. After you balance the equation, you would say that magnesium here have a coefficient of 2, and oxygen have a coefficient of 1, and magnesium oxide have the coefficient of 2. This means that for every 2 moles of magnesium, you need 1 mole of oxygen, and 2 moles of magnesium oxide would be produced. So how exactly does it help with calculating which reactant is excess or limited, and when you want to calculate the mass of the substances? Let's say that you have let's do the molar mass. Let's say you have 96 grams of magnesium. And you have 19 grams of oxygen. And you want to say which one is excess, which one is limited. So first of all, you do um, the molar mass of magnesium in this case is 48 because magnesium is 24 and times 2 equals 48. So, and you apply this formula over here, N equals M divided by capitalized M. And so how many moles of magnesium do we have for 96 grams of magnesium? N equals 96 divided by 48. 48 is the molar mass, equals 2 moles. And since the ratio of magnesium, the mole ratio of magnesium versus oxygen is 2 versus 1, for every 2 mole of magnesium, you would have 1 mole of oxygen. So you do 2 moles divided by 2, which is the number of moles needed to react fully with 96 grams of magnesium. The number of moles of oxygen is 1 mole then. And you then apply this formula over here. And you times it by this formula over here. You times it by 16. You times it by 32 because the molar mass of oxygen is 16 times 2, which is 32. And times it by 32 and you get 32 grams. Now, 32 grams is bigger than 19 grams, meaning we don't have enough oxygen to react fully with 96 grams of magnesium. So oxygen is a limited reagent and magnesium is an excess reagent. So if you want to calculate the mass of magnesium oxide that's produced, you just go because you have you just go, since that's limiting reagent, we need to adapt to this limiting reagent, and you figure out how many moles of oxygen you have, which is 19 divided by 32, and that's and you need to times it by 2 because the mole ratio of oxygen versus magnesium oxide is 1 versus 2. So you times it by 2, 19 divided by 23 times 2. Then you times it by the molar mass of magnesium oxide, which is 24 plus 16, which gives you a number of 47.5. That's how many grams of magnesium you have produced in this reaction. Finally, let's move on to hydrated salts, water of crystallization. So it's basically salts that are also loosely attached to water molecules. Let's say you have this compound, cobalt chloride, well, the hydrated version of it would be cobalt chloride 6 H2O. And the above hydrated salt has a molar mass of well, just to add them all together, the molar mass of cobalt is 58.9, and the molar mass of chloride is 35.5. Because it has 2 chloride here, we need to times it by 2. And then you add, because you have 6 water here, so you do 6 times brackets. Inside the brackets, that's the molar mass of water, which is H2O. The molar mass of H is 1, and you have 2H, so you times it by 2. The molar mass of O is 16, you times it by 1, since you only have 1 O. And you get 237.9 as its molar mass. The unit is grams per mole, as we mentioned before. So how would they test you on this? Sometimes they would tell you what the formula is and give you the mass of the substance before heating, and you need to figure out the mass after heating. This is and the way you do it is by so you know the formula, and you have the molar mass, and you have the mass of this compound together. So you do the mass divided by molar mass. So whatever the mass is, you divide it by 237.9 in this case. And that would give you sorry, it should be you should calculate the percentage composition of water in this compound. So you just do this part 6 times 2 times 1 plus 1 times 16 divided by this part, and you figure out the percentage composition of water in this hydrated salt. Then you times it by the total mass before heating, so you will get the mass of water in this compound. And then if you want to know the mass of this compound after heating, well, you just do the original mass before heating minus the mass of water, because water is what they lost to evaporation after the heating, and then you get a number. And sometimes they could ask you, what's this coefficient over here? And the way you do this is by so you would know the mass before heating and the mass after heating, and you do the mass before heating minus the mass after heating. It would equal to something, and that something is the mass of water in this compound. Then you do the mass of water divided by the molar mass of water, and you get a number, which is the number of molecules of water you have in that compound. And speaking of this kind of chemical compounds, they could be written in molecular formulas or empirical formulas. So with molecular formulas, it's the actual formula. So say I have this substance, say to H2O4. This is a molecular formula, and if you want to convert it to an empirical formula, you would just get the simplest ratio of whole numbers, which would be say HO2. You divide all by 2 so that you get the simplest whole number ratio. That's 2 over here. Okay, thank you for watching.